Hello, everyone. Welcome back. We got this one last lecture. I know it's been a little bit since I made a video. Finally had some time to do it, so we're going to knock it out today. So, where we last held off of was when we made a little scatter plot here of taking a look at the wins and the point differential for NFL teams in the 2024 season. Um, and it makes sense. Teams with a more positive point differential are going to win more games. But I just wanted to give you a little tutorial on how to just make a cool plot with NFL team logos just by using some web scraping techniques. Today's gonna be a little more on the data science side of things, just going over where to look for with the models, and I'll show you how to use a model for an example. It'll just be a simple linear regression. Since this is kind of an introductory course, but by no means you should be limited by what I go over today. So a lot of the models that you would use in data science is from a library called scikit-learn. So if I look up scikit-learn, see a website pops up here. If we click on it, so scikit-learn is a Python library or a Python package that has a bunch of models stored inside of it. So it has things like linear regression, random forests, gradient boosted trees, logistic regression. So the main models in data science that you deal with are either classification, so it can be binary outcomes, it could be multiple classifications like a certain type of breed of dog. You have regression, which is more continuous patterns, could also be time series analysis. And what that could be is like a linear regression model. It could even be some sort of gradient boosted regression model, which is like a bunch of decision trees or random forests, ridge regression. You also have clustering, which you have like k-means, DB scans. You have clustering, which is like unsupervised learning versus supervised. A lot of terminology to throw out there, but we're going to keep it simple. I just want to go over the layout of this website because you're going to be using this a lot if you're going into the analytics side of things. So, see if there's anything else on here. The main thing they can look for, so if you're curious about how to install it, they have an installation guide on here. I'll go over how to do that quickly on the notebook. Main thing with these packages, as I mentioned before, is to look for the API reference. This is where you get everything, all their functions. So let's go to a linear model and we'll do linear regression as our example. So they have a class from the linear model called linear regression, which most of you all know it's fitting a straight line through certain points of data. Um, it's the most primitive regression model that I can use, and it's a good one to start out with to learn, so that way you know how to deal with like error metrics and whatnot. Um, Not too much to go over here. I just want to show the models and the available models that you have. Another thing I want to show you is the metrics. So a lot of these, when you make models, you want to know how to evaluate them. And scikit-learn has a bunch of pre-built error metrics they can use. So a lot of these at the top here are more so classification error metrics. Let's go down to like a regression one, like R squared score, which is just how well your model explains the variation in the data. It takes in the true and the predicted variables. Has a bunch of other parameters too, which most likely not used in majority of cases unless there's an odd case. Um, Another one's like root mean squared error. Should also be a mean squared error, or maybe I passed it. Yeah, like mean squared error here. But yeah, trying to see if there's anything else on here. You can also build pipelines, which is cool. Just like building one model on top of another. So you have like a scaling and then creating a support vector classifier. That was one of the examples I provides on here. The last thing I can show too is the pre-processing steps. Maybe not here, because a lot of these pre-processing is like scaling. So say you have a large variation in data and you don't, and you're feeding it through like a linear regression model. Well, that linear regression model is going to output high variation. So scaling the data could normalize it a little more so that way the model's a little better at predicting uh, the particular target variable. But that's not really what I'm looking for. Experimental feature. No, it won't be under feature selection, but it also has a tools they can use to select for certain features if you don't know what features to use. I think it's under model selection. Yeah. So under model selection, there's this thing called train test split. So where train test split comes into handy is if you want to build a model, train it on a certain subset of the data, make sure things are running smoothly before you actually predict it on real world data. This is where you can split it into like a training and a testing group. You can also have like a validation group. And this would be like an example. So you have like the X train, X test, Y train, Y test, train test split. Again, this is kind of a lot, and I'm not really going to go over all of these in one video. It's just I'm providing a resource for you to go around, to look around, play around with. If you want to take a look at some examples too, scikit-learn has some. I'm just going to show an example simple linear regression model. So some libraries we're going to want to install are scikit-learn and then NumPy for array manipulation because NumPy is pretty fast and awesome. All right, so we're going to want to build a model, and let's just build one like a simple linear regression model of we're trying to use point differential. I guess I kind of have this. We can do like how many wins determine point differential, I guess, since we already have point differential on the Y, wins on the X. We're saying point differentials dependent on wins, so we're going to try to use wins to predict point differential. Maybe not the best model, but just an example. So we're going to do from sklearn.linear model. We're going to import linear regression. And then we'll do regression equals linear regression. And what this is doing is just instantiating a class linear regression. So it's already got a bunch of or the linear regression algorithm's already built into this linear regression class, so you don't have to worry about manually building one yourself. And now we're going to define like our x and y. So x is going to be the data frame, which I'm going to need to rerun this code to get it. Hopefully this runs smoothly. The best part about programming is running things and running into errors. All right, we'll do test output here. All right, sweet. So we got our data frame. So we're going to do df, and it's, remind me, it's w. And then our y, or our target, it's going to be point differential, which is the PD there. So if regression, we've got to fit it, which was an attribute. I'll show it on here. So regression has some functions built into it. One of them is called fit, which is just fitting the linear model that's running uh, the regression model through. So it'll be reg dot fit x and y, because that's what these two parameters take in. And we'll run that. And it's not fix, it's dot fit. And we've got a 2D array error. And a way to bypass that is by indexing it again. Uh, the so it's expecting a two-dimensional array and got one. So if I subset the wins once, this is a 1D array. If I subset it again, this is technically a 2D array. I wonder if this works. Nope. So essentially just creating like a series with the 0 and the 13 for the wins. Okay, sweet. Now to make predictions on it, we can call that predict function here, used to predict it. This takes in our x. Literally just do this since we're kind of training, we're not really training, but we're fitting it to this data and we're just going to make predictions on it to see the outputs like so. And we'll save that as our predictions. And then let's just check the shape. So yeah, 32 teams with one row. I mean, one column, which is the predictions. Okay. So we have our Y true and our pred now. So what if we want to take a look at some error metrics? Actually, before I even do that, let's take a look at the regression model. So if we take a look at the coefficient, so it's about 27, and then it should be, I think, dot intercept. There we go. And I'll just show you what that formula would be. So it'd be y equals the 27.437x minus 233. 0.211. So this is the regression formula here. We have the correlation coefficient, and then we have the intercept. Now let's take a look at some error metrics. So we'll do from sklearn metrics import. We'll do mean squared error, and then we'll do r squared score. And we'll just go ahead and just do r squared score first. So we'll do r bam score, and I'll do r squared score. And then we want our y true, which is just y, and then our y pred, which is our predictions. We'll print, we're going to do root mean squared error. So on average, how far off are our predictions from the actual scoring differential here? To do that, we need to just take the square root of the mean squared error. That, oh, I need to run this. And I need to import numpy's np. Since np is not defined, just got to import numpy as the alias. All right. So the percent of variation. So wins is a pretty good predictor. It accounts for 82% of the variation. And the root mean squared error is not bad. It's on average, each point is about off by 46. So the 49ers, for example, could be 46 points. The prediction could be 46 points up or 46 points down based off the average. Um, it would just fall within that range. So not too shabby for a model. We could also plot it as well. So I'm gonna need to rerun these. I forgot this is gonna take about a couple minutes. So I'll get the code ready. We'll do plt.plot red. I'll say color. It's red. And while that's running, see if I can think of anything else to go over with scikit-learn. It's a big library to get used to. The main things that I didn't really go over that I can't go over while this is running is like the train test split. So how that would look is like X train, X test, Y train, Y test equals train test split. And then you'd have your X and your Y, which X is going to be all your features, Y is going to be your target. And then I always specify the test size. It's default to about 20%. So it only, so you have like 100% of the data. Let's say like 20% is taken off of that entire data set and put into these test variables here. And then if you want to get the same results, you specify random state. So in honor of Jackie Robinson here with the random state. But if the random state, that just means if you run this over and over again, you're gonna get the same splits as long as the features and the target are the same throughout. And perfect timing. This is done running. Let's plot. Okay. Probably. I think there's a way I can fix this. Because I think it's doing, oh yeah, it's incrementing by that, so it needs to be on that. Okay, so we just make this part of our data frame. So I'll do that. Let's do that here. We'll say df pd red equals to reg.predict, and we'll say df and wins. Yeah, and wait, value error. Oh, yeah. I have to do this again. Bam. All right. Now this should work. PD pred. Oh, what? Still same thing. Still the same thing. I knew that wouldn't work. Sorry, it's 11 o'clock at night and I'm trying to figure this out. Thought that was that should not be the case. Maybe it's there we go. Just needed to make wins the x-axis. Okay, that looks better. So now you can see how off these wins are. So look, the Chiefs would be predicted to be towards where this red line is, but because they cheat a lot, they're down here. So they're winning a lot more games than they should be. Those darn sorry sons of guns. All right. Well, enough with my venting. That's all I really wanted to go over for today. So thank you for your time. If you have any questions, just reach out to me either in Discord or leave a comment on the video. Take care. Not sure when I'll do another video, but who knows? We'll see.